So now we have a method, the MacCormack method for the solution of Navier-Stokes equations. Can it be applied for all cases? Is this a panacea? Is this a method that we can use to solve all the equations? Let us examine the issue. This we have seen is the predictor corrector step of second order accuracy both in time and space. So that is a very desirable aspect, and it is also both the steps are explicit. N plus 1 bar is given only in terms of n here, and n plus 1 here is given only in terms of n plus 1 bar, and we have a sequential evaluation of all the variables. So this looks like a good way of solving the equations, and it has proved to be successful. But like many explicit methods, this has stability requirements. You cannot have an arbitrary delta t and delta x. Here we have delta t, delta x, delta y, delta z, and we know that this equation, although we have put it like this, has an advective component, and we also have a diffusive component coming from the shear stresses, and we also have the source term coming from the pressure gradient. Okay, you have a pressure gradient here and here and here. Fortunately for us, the pressure gradient is not a function of the variable that we are solving in a direct way. Okay, we can see that pressure is influenced by this, and pressure is also given by the density. So in that sense, it is nonlinear. The source term is nonlinear, but it is not directly coupled to the evaluation of rho u, rho v, rho w in such a way that it appears as a variable in terms of rho u, v, w here. So in that sense, although the pressure is a nonlinear variable in terms of the density through the equation of state for that particular fluid, as far as the equations are concerned here, it is not appearing as a source term where it is a function of phi. Okay, so if you write this as a general scalar transport equation, then the source term as a function of the scalar variable phi is not very clear in this. So we can only say it is indirectly, implicitly coupled into this. So we have a source term which is independent of phi here, and we have an advective term and a diffusive term. So we can expect something like a Courant number kind of limitation coming from the advection term, and we have for the diffusive term we have the diffusivity times delta t by delta x square, that kind of combination of limit that should come through this. And we not only have those two, we also have the multidimensionality. We have x direction, y direction, and z direction. So we can expect further degradation of the stability limit, especially for the diffusive term. So what is the overall stability condition on this of this method? It is not easy to evaluate, and as we go to more and more complicated things, the stability condition probably can be evaluated either heuristically or empirically. It can only be estimated. It may not be possible to to evaluate this explicitly or through a closed form type of solution, given especially the fact that the pressure, one of the variables that is coming here, is coming through indirectly through an algebraic equation of state, the form of which is not readily evaluatable. Okay, so from this one can only, in a semi empirical way, maybe we can write down a stability condition, and the stability condition for this is expressed in the form of delta t, delta time should be less than delta t CFL. So that is the Courant-Friedrichs limit. This is in the case of inviscid. Okay, let me put this as times a factor of safety sigma. Let us put this as sigma SF divided by a function which is based on the Reynolds number, and it is given, it is estimated to be 1 plus 2 divided by Re delta. So you have the overall stability, that is the maximum delta T that you can have here, is obviously very closely linked to the inviscid flow, in which case the viscous stresses do not come into picture, it becomes a hyperbolic function. And this inviscid CFL condition for the delta T can be written as the delta T CFL inviscid meaning obviously viscosity is 0, given that we have 3-dimensional flow with not necessarily 0 UVW components. Okay, so it is plus A times square root of 1 by delta x square plus 1 by delta y square plus 1 by delta z square, and this whole thing inverse. Okay, so one can say that if it were 1-dimensional flow, okay, so that V is 0, W is 0, and delta y and delta z do not come into picture, this delta T CFL inviscid becomes 1 by u by delta x plus A by delta x. Okay. So if u is very small compared to this, then this becomes delta x by A. Okay, so this is in the case of 1-dimensional thing. This is just to illustrate the form of this delta T. Okay, so the delta T is delta x divided by A, where A is the speed of sound, and is given such that A square is equal to d rho by dp. Okay, under isentropic conditions. Okay, so in that sense this is related to the equation of state, and so this is a property of the medium itself, speed of sound in the medium. If it is a gas, it is a gaseous medium and mixture of gases, then the corresponding thing. So what we see from this is that the inviscid flow delta T is now related to the speed of sound, and it is also related to the velocity of the flow, and in 3 dimensions it is not only this, but you also have a contribution coming from V and W, and we also have these things. So you can say that delta T CFL inviscid 3D is less than delta T CFL 1D. Okay. Now this CFL is what is coming here in the 3D, and this is being multiplied by a factor of safety. Sigma SF is a factor of safety because we can't evaluate this exactly, and this is less than 1 for it to be a factor of safety, and is typically taken to be about 0.9. Okay, so that means that the delta T that you can use for this is less than what you can use in the 1-dimensional limit, and it is less than that because you are using a factor of safety, and this whole thing is less than the 1-dimensional limit because you have a viscous effect coming through the Reynolds number, and the Reynolds number delta here is called the mesh Reynolds number. and this is the minimum of Re delta x, Re delta y, Re delta z, because now we have 3 different velocities and 3 different spacings, where Re delta x is defined as u delta x by nu, where nu is the kinematic viscosity, and similarly Re delta y is obviously determined by v delta y by nu, and so on. Okay, so you evaluate. So if you want to find out what is the minimum delta t that I can use, then it is highly dependent on the local values of u and the local value of delta t that you have. So you evaluate at that particular point. So we are looking at delta t at a particular grid point ijk. So you evaluate u ijk delta x, and then v ijk delta x and w ijk delta x. So based on these you evaluate the and you take the smallest of these as the mesh Reynolds number, and you put 2 by the smallest of this, and that gives you the largest possible of the contribution from the Reynolds number thing. That is added to 1, so this is obviously greater than 1, and so the delta t that you can actually use is now evaluated based on this formula for each of the points throughout the domain you have for all ijk's, and you take the smallest of those values in order to ensure stability. Okay. Some people may say, okay, you take the largest value because it is an estimate, and for example in case u is 0, if one of the velocity components is 0, then this becomes very small, this becomes very large, and delta t becomes almost 0. Okay. So to avoid those kind of things, you can take a representative value of this, but the point that remains is that the delta t CFL that we have for a pure convective thing, which is based on the delta t maximum is delta x by the wave velocity. In this particular case it is delta x divided by the speed of sound, and we know that speed of sound is typically high, so that means that delta t is small, and the actual value is made smaller by the fact that you have 3 dimensions, so that the CFL value itself is smaller, and you have an additional contribution coming from the Reynolds number, that is the viscous stress component, and there is also an additional factor of safety which is coming less than this. So because of this, the delta t ijk is less than the ideal value for the 1 dimensional case, and we have to choose the smallest of the delta t's for all the grid points to progress further in this. So based on this consideration we choose the delta t, and once we fix the delta t, then we substitute this into each of these, and then we go from n to n plus 1. At the end of n plus 1 we re-evaluate all the factors contributing to the delta t, and then we pick a new value of delta t, and then we go and proceed further. So as you go from n to n plus 1 to n plus 2 to n plus 3 and so on, the delta t value may change. It may become lesser or it may become greater depending on how the velocities are changing, and how they are feeding into the inviscid limit and also into the Reynolds number here to get the overall viscous limit of CF, the delta, the stability condition, which is an estimated quantity. Okay. So this method is a workable method, and with this stability condition given like this, it is a completely workable method in the sense that you can go ahead and solve this with some initial conditions, and then go on up to to investigate the evolution of the flow variables as time progresses. Now can we extend this to incompressible flow, because we have said that is a main area of interest, especially in chemical and process industries, where typically we are looking at Mach numbers of less than 0.3. So in which case you have very little compressible flow effect. So in such a case, what happens to this? What happens especially to the delta t? We can have the method here, but in order to implement this we need to make sure that the delta t is smaller than whatever this limit says. Now as the flow becomes more and more incompressible, that is d rho by inverse, okay, yes, this is the speed of sound. So as the flow becomes more and more incompressible, the speed of sound in that medium, it increases more and more. For a purely incompressible flow, the speed of sound is infinity. Okay. Now what happens when the speed of sound increases? As it increases, this increases. So 1 by this we have put here 1 by this increases. So as A increases, this becomes small and this becomes large, so that effectively the delta t inviscid limit is given by delta x by A, and as A increases, delta t inviscid decreases. So as A increases, delta t CFL decreases. So and as the flow becomes more incompressible, then the delta t that you can employ for this method decreases, and you can take smaller and smaller delta t's only. Okay. And in the incompressible limit, A is infinity, so that means that this method will not work. Okay. So the explicit method, which typically has a constraint, a Courant number type of constraint, and in the case of viscous flows we have additional constraints. So it cannot be directly applied to incompressible flows because of the stability requirement. Now if we can't apply the explicit method, can we go to implicit method? Okay. Because we know that implicit methods many times have unconditional stability. In fact, there is an implicit form of the MacCormack method itself, and there are many other methods, and even explicit and implicit. All of them, all the explicit methods have typically some sort of constant, especially when you are dealing with a set of equations in 3 dimensions like what we have here. And when you go to the implicit method, for the given scalar transport equation with constant coefficients, you can have unconditional stability. But if you have too large a time step, if you take delta t as being large, for example 10 times the inviscid limit that you get from these things, then the error introduced in the time evolution will become large. Okay. Because any scheme that you have here like this has, for example, this has second order error with respect to time. So if as delta t becomes large, the error in the evolution of the evaluation of the time variation, okay, the time dependent term will become large. And the problem that we have with the coupled equations, with the Navier-Stokes equations, is that if you want to evaluate, for example, the u velocity, not only do you have u, but you also have rho, which is indirect p, which is indirectly coupled to u, and then you also have v here and then w here. So that means that in order to evaluate u, you need to know all the other variables that are incorporated in this. Now if you were to solve only the u momentum equation, then your implicit method may give you unconditional stability. But in order to do that, you also need to simultaneously solve the v equation, w equation, and if you make large errors in the evaluation of u because you have used large time steps and therefore you have misrepresented this, then that plays havoc with the values of v and w, which are integral part of this. When you go to the evaluation of v and w equations, you are carrying forward a large time error and in the evaluation of u, and therefore since the evaluation of u also affects the evaluation of v and w, the coupled nature does not allow you to have too large time steps. Okay. So you can typically have only maybe 5 times or 10 times the implicit limit for explicit limit for an implicit calculation, and that arises primarily because of the intercoupling of the Navier-Stokes equations. So direct application of these kind of methods which have an time step limitation arising from compressibility considerations like the speed of sound limit that we have will not allow us to extend these things directly to incompressible flow. So although this MacCormack method is quite useful and it has been applied for the solution of the coupled equations, it is not readily extendable to fully incompressible flow calculations, because the corresponding time step that is required for this will become impractical. So we need to find new methods, new ways of doing this. So that is where the straightforward extension of methods developed for compressible flow to incompressible flow calculations typically fails, and we would need to look at the special difficulties that are associated with incompressible flow calculations to arrive at methods which are tailored to those kind of flows. Okay, so let us just write down what the equations of incompressible flow are, and then we can understand what the difficulty that is there is. We know that for incompressible the Navier-Stokes equations become like the continuity equation. Let us say that we are dealing with two-dimensional flow, so as to make the equations a bit smaller. The continuity equation is dou u by dou x plus dou v by dou y equal to 0, and the x momentum equation is dou u by dou t plus dou by dou x of u square plus dou by dou y of u v equal to minus 1 by rho dou p by dou x plus nu times dou square u by dou x square plus dou square u by dou y square, assuming constant property, so that mu the viscosity, the kinematic viscosity is also constant, and rho is obviously constant because we are considering the flow to be incompressible. And we can write down the y momentum equation as dou v by dou t plus dou by dou x of u v plus dou by dou y of v square is equal to minus 1 by rho dou p by dou y plus nu times dou square v by dou x square plus dou square v by dou y square. So we have three equations and we have three variables. And what are the variables we have? We have u, v and p. So from a point of view of the closedness of the problem, we have as many equations as a number of variables, so that in principle we do not need any other information except of course the initial and boundary conditions as per requirement, as per the nature of the problem and so on. Okay, so in principle we should be able to calculate get a complete solution of UVP variation with x, y and time by solving these equations with the appropriate initial and boundary conditions. Now when we want to implement this in our standard CFD form, we can write the corresponding things as a scalar transport equation like this. this is a standard form that we have in 2 dimensions. We can put these equations in this form, okay. Now where phi becomes either u, v and thing like that. Now the difficult thing that we see here is that now the x momentum is a statement of the conservation of u, the velocity component in the x direction. Therefore we expect that this equation should be solved in order to get u, okay. So the value of u is more or less determined by the momentum balance, because u represents the momentum per unit mass in that particular direction. And similarly one can say that the value of v, that is the vertical velocity component, which is also the specific y momentum, is determined by the y momentum balance. So we have a natural equation for the evaluation of u and v, okay. So out of the 3 variables we have the x momentum equation to get this and y momentum equation to get this. So the remaining variable is p, pressure, and the remaining equation is the continuity equation. So this means that we have to get p from the continuity equation, and the difficulty is that there is no p term in this. Pressure is not appearing in the continuity equation here. So when we consider incompressible flow equations, if we make use of the u momentum equation, x momentum equation for u and y momentum equation for v, then we have the only other equation, the continuity equation, left to evaluate pressure, and unfortunately pressure does not appear in the equation at all. So that means that you cannot get pressure by solving this equation. We do not have the problem in compressible flow, because in compressible flow we are not solving directly for pressure, we are solving the continuity equation for rho and the x momentum equation for u, y momentum equation for v and z momentum equation for w, okay. So we are making use of the natural equations here, and rho appears in the continuity equation because you have d rho by dt plus all those things. So the continuity equation, which is used to evaluate the 4th variable, which is rho, has the corresponding variable appearing as the main term, okay. So the continuity equation for in a compressible flow is d rho by dt plus d by dxj of rho uj equal to 0, okay. So from that point of view we can therefore write this is equal to minus of this, and this can be used to evaluate rho ijk n plus 1 from rho I and so on, okay. So in that sense for compressible flow we have no such problem, because the 4th equation is used to evaluate the 4th variable, and the 4th equation does have the 4th variable as the primary variable in this, okay, as the main variable in this, and we evaluate the pressure from an algebraic equation of state from known density and known temperature. So the difficulty of evaluation of pressure does not arise in compressible flow, but it arises in incompressible flow because of this specific problem, okay. So question is how to evaluate pressure. So and we know that the speed of sound is linked to the variation of density with pressure, okay, but for an incompressible flow that linkage between density and pressure is not there. It's no matter what the pressure is, the density does not change. So as far as incompressible flow equations are concerned, density and viscosity are imposed variables, they have no relation to the flow variables, which are u, v, p and u, v, w and p. So even if pressure changes, the density does not change in incompressible flow. So in a way incompressible flow has no sense of absolute value of pressure, it is only the pressure difference, that is the pressure gradient, that comes into picture in incompressible flow. So that marks a major difference between compressible flow and incompressible flow, that is the feedback effect of the pressure on the density and through the density onto the equations is non-existent in incompressible flows. Okay, it is the relative pressure difference that affects the velocities, and of course the velocities have to change in such a way that they also obey the continuity equation. So we have only an indirect linkage between the pressure and the continuity equation. That linkage has to be somehow brought into play when we want to solve these three equations together for this. Okay, one can say, why not make use of the continuity equation for u and this equation for p and this equation for v. That kind of thing is not possible. It is like trying to control a tiger by holding its tail. Okay, then we know that you cannot control the tiger just by holding the tail, because it will probably pounce on you and then eat you up. But if you were to hold it by the neck and then do something there, then you can definitely control it. Okay, so by using the continuity equation here and then the pressure here will lead to that kind of situation. Because of the strong intercoupling of the three equations, it is not possible to do in other way than to use the primary equations for the primary variables. Okay, so the most logical thing is to solve the x momentum equation for u and the y momentum equation for v, because u and v represent the specific momentum in the two respective directions, and we expect that momentum balance will give you the u. And unfortunately we cannot solve these equations unless pressure is specified, and we can get the pressure only from the continuity equation, but the pressure is not there as a variable in that. So how to get around this difficulty? There are several methods that have been developed specifically for to get around this, and one of these things is to introduce artificial compressibility. Okay, so we say that since we are not able to get pressure from the continuity equation, if we introduce an artificial compressibility, for example we say that pressure is given by rho by say beta, and where beta represents the compressibility, so that if you now introduce a term like, let us put this as rho star. Okay, so you introduce d rho star by dt into the continuity equation, and you solve this for rho star I n plus 1, and once you get the rho star I n plus 1, you can go back to this equation and get the corresponding p here. Okay, so in that way you can introduce an artificial compressibility and add a term to the continuity equation which allows you to evaluate this d rho by dt as a function of the changes in velocities, and therefore thereby you are coupling the equations. Okay, coupling the pressure and the continuity equation with the momentum equations through this artificial compressibility. Now this is only a fictitious thing. Okay, this is something that we are adding. It is not the true density, it is not the true coupling, because there is no coupling between pressure and density for incompressible flows. So the resulting solution is not correct. Okay, for all the trouble that we take, we get a variation of uv p with respect to time and also xy, but we know that it is not correct because we are solving the wrong equation. This term should not be there. Okay, but the steady solution that we have will obviously have the contribution coming from this to 0. So under steady conditions this term will go to 0, and the steady velocity field that we get uvp xy, okay, where the time is not there, is such that it will satisfy all the three equations. Okay, the three equations without this extra term. So the artificial compressibility method is a way of getting the correct solution which is valid only for steady flows, but it will not work for unsteady flows, but by introducing an artificial compressibility you can create an artificial linkage between a fictitious density and pressure, and we can make use of an extended form of the continuity equation to solve for that artificial density term, and then bring into that to create thereby a bridge between the pressure and the velocity variables through the continuity equation. So this method will work, and we will look at this method in detail later. It has been successfully applied for many steady flow solutions. There is another possibility. Since pressure is the headache variable which is causing us all the headache, why not just eliminate it from the Navier-Stokes equations? If we eliminate it, then we can come up with a set of equations which do not have pressure, therefore we do not have to solve it. If pressure does not appear in any of the equations, then we do not have to solve it. Is it possible to eliminate? It is possible to eliminate pressure. For example, if you take the derivative with respect to y of every term in the x momentum equation, and you take derivative with respect to x of every term in the y momentum equation, and then you subtract this from this, then okay, there will be changes here. This term here will have dou by dou y of this, and this term will have dou by dou x of this. Now when p is continuous and rho of course is constant, then this term will become minus dou square p by dou x dou y, and this also minus dou square p by dou x dou y. When you subtract the two, these two will cancel out, and the resulting equation, that is the equation resulting from the subtraction of the dou by dou x of y momentum equation from the dou by dou y of the x momentum equation, will only have velocity variables with respect to x, y and t, and they will not have any pressure. We will show that we can define a new variable called vorticity, and using that we can get a vorticity transport equation which looks very similar to the generic scalar transport equation for which we have come up with discretization methods. Okay, so we solve that vorticity transport equation for the vorticity, which is a combination of the velocity gradients, and we can also introduce the concept of stream function, and using the stream function we can eliminate this, and we can come up with a new set of variables, vorticity and stream function, approach in which the velocities do not appear at all and the pressure do not appear in the combined vorticity and stream function relation. So the three equations that are appearing here can be clubbed into two equations which are partial differential equations which can be solved to give the vorticity and stream function, and from these things we can get velocities and velocity uv components, and we can solve an additional equation for pressure that is called a Poisson equation for pressure, which can also be derived from these things. Okay, so we evaluate UVP, that is the velocity components and pressure, from these equations in a roundabout way. Okay, we transform these three equations into two coupled equations involving vorticity and stream function. We solve them using standard methods because these equations look very similar to our generic scalar transport equations. We solve them using the standard methods, and which will give us the stream function and vorticity, from which we can deduce the values of u and v, and once we deduce the values of u and v, we bring them back here, and then we do further manipulations of this, and we derive a Poisson equation for pressure which has uv as variables and the velocity gradients as variables. And since we already know the velocity gradients of or since we already know the velocities u and v, we can evaluate the gradients, and then we can convert this into a Poisson equation for pressure, and we solve that equation to get pressure. So the computation of UVP is now broken into 2 steps, maybe 3 steps. One is solution of vorticity and stream function together in the form of 2 coupled partial differential equations. From that, reducing U and V, and from this solving another partial differential equation for pressure. So that kind of approach is also very widely used, but this equation is valid only for when you can define a stream function, and stream function is defined only for 2-dimensional flows. So this method is applicable only for 2-dimensional flows. This method is applicable only for steady flows. Okay, so this is applicable for steady 3-dimensional flows. This is applicable for 2D transient flows. Okay, in that sense, both the methods cannot be used for the generic case of transient 3-dimensional flow. Okay, so now if you want a transient 3-dimensional flow, then you have to do something more, and there again we make use of further manipulations of these things to get that equation, pressure equation, which we already obtained as part of the vorticity stream function method. So we solve for the momentum equation and pressure equation in a coupled way. Okay, and so that is called a pressure equation approach. This is applicable for transient 3D, and the fourth method, which is much more often used, especially for incompressible flows and especially for chemical and process engineering applications, is instead of solving for pressure equation, pressure directly, we solve for a pressure correction. Okay, so we derive a pressure correction equations by manipulating these equations, and then we solve for the pressure correction, and we can come up with an overall solution approach which is specifically tailored for incompressible flows. So all these 4 methods and many variants and other methods are derived specifically for incompressible flows to get around the problem that is unique to incompressible flows, in the sense that pressure is not coming as a direct variable in any of the major equations. Okay, there is no equation for pressure in this, so we have to reformulate in a certain way, in a different way, so as to recover pressure from the continuity equation. Okay, so that is how we can evaluate the flow variables for incompressible flows, and the last 2 methods are applicable for the general case, whereas these 2 methods are specifically for either steady flows or 2D flows, and the artificial compressibility method is such that you can directly apply the methods developed for compressible flows, like what we have seen, the MacCormack method, either in its explicit form or implicit form, can be used for artificial compressibility thing, and the other type of methods also can be used for vorticity stream function approach, but this is only for a 2-dimensional case. So, and these are the special methods, but the specific aspects of the solution are still common to all the things, because all the 4 methods will involve either the generic scalar transport equation, which is a time dependent term, advection, diffusion, and a source term, or in these 3 cases, in addition to that at least one scalar transport equation, you also have an additional either Laplace equation or Poisson equation that has to be solved, and Laplace equation or Poisson equation is a special form of the scalar transport equation for the case where you have for the steady case. Okay, steady non-convective case or steady diffusive case is a Poisson equation when you have source terms. Okay. So, in that sense the methods that we have developed for the general scalar transport equation are still applicable and they can still be used here, but we have to come up with a rephrasing of the equations of the governing equations in order to be able to solve them for incompressible flow. So, in the next lectures we will look at these methods and see how these can be implemented.